Okay, excellent. Well, we're actually ahead of schedule. Amazing. So do I get 14 minutes, Parker? Well, thanks everyone for coming. It's really great to be first. But I really like this venue. This is like the third time that I've presented here, and many of you have been here much longer, but I really appreciate this venue. It's a good place to show like work in progress, especially. So I hope you also enjoy it. So the first presentation I'm going to share is one of the larger grants that we have, that my team has from the ARS TDI funding, which is about developing material-aware robotic processes for machining, inserting, and fixing prefabricated mass timber connections. And this project, this is the team that works on the project. Myself, my former graduate assistant, Braden Lowry, who now works at Timber Lab, and we would love it if you would come back. And also Professor Ross Hatton, who's an associate professor in College of Engineering and Robotics here at OSU. And then we have also now a new team member, a PhD student from also from the robotics program that's going to work pretty heavily in the second year of the project as we kick that off. We also have a number of industry partners in this that are non-funding partners, but have worked with us on developing the project and provided consultation. So Timber Lab Swinnerton and KTM Research, which is an automation engineering company in Portland, also run by OSU alumni. More recently, we've started working with Simpson Strong-Tie and two producers of automated screwing systems, Weber and M6 Revolution. And I'll explain where they come in a little bit later. But the main goal of this project was to look at this, take one specific challenge that we've identified in mass timber production, and see how we can use like new developments in robotics to try to automate that with better quality than would be particularly done in just like a sort of pure integration or like robotic integration steps. So we settled in talking with Timber Lab and also Swinnerton and many others, we settled on this idea of using the robot to place and then also fix concealed beam hangers into glulam beams or MPP beams. There's a number of reasons why we focus on this, but I think we all agree that it is a task that is like so far now not automated. And while there's been a lot of advancements in automating CNC production and how digital tools can be used there, these sort of secondary steps are typically now still done manually. So in the first year, we've done some laboratory testing and the like basic setup of this, and then we're going to like sort of continue on certain paths that I'll explain later. Part of the first year was also like talking a lot with these companies. So we visited Timber Lab. We've had people from Swinnerton visit our lab to really try to understand in more detail how this is done now and what the main constraints are. We also visited and talked a lot with Simpson Strong-Tie, who of course approaches this problem from like a production or product production point of view, which is really different from how mass timber companies are doing it. And we've also talked a lot with the people that make the screw guns. And what we've like figured out is basically two sort of key strategies. Is that we're going to use force feedback, which you can think of like the robot actually feeling where it is, rather than like looking with a vision or a camera, as like the main way to like find and locate where the robot will place the parts, because vision systems are really tricky in these, even in prefabrication factories. And that the second point is that we want to have the system be like relatively adaptable. So not thinking of it as like strictly like inline in like a conveyor system, but really being able to deal with the variation in product sizes and like parts that need to be installed. And so we mocked up like a very simple system like this in our lab using a small like collaborative robot that has a force torque sensor inside of it. And I'll just walk you through how this works. We took one of the like more common Simpson Strong-Tie hangers that's installed with 3 or 6 inch screws. And then we mocked this up. So like I'll show you a video, but we'll walk you through it. Like the robot basically approaches. In this case, we give it the plane, like, so we give it like a hint as to where to look, but we're working now on like expanding that. So like if you come next year, you can basically like move the beam all around and the robot will find it. But now we give it a plane and then we let it do a very simple test to basically find the top edge. In this case, it's inside a pocket, but later it will be different. So it finds the pocket like dynamically, feels where that is, then it finds side to side, and then it pushes in to find the end. And then it can be fixed or replaced with a set screw. And right now we do that like completely manually. So it's a sort of co-robotic operation, but we're also looking at how that can be done with another robot. In terms of a video, it looks kind of like this. This is, of course, digital. So it goes up. And it has a certain range of adaptation, but then you can like hardly even see where it's sort of feeling for this edge because it happens so quickly. And then show the, yeah, and then another robot can come in and screw in the set screws. And then in our lab, like many of you that were at the Mass Timber Conference, you probably saw also this demo that was in the corner of the research symposium. So here we mock it up with just some 3D printed parts. So again, it's like feeling the top edge. And we also will have this in the research showcase at Emerson later, so you can see it working or not working. And you can also play with it. It's quite fun. You can like pretend you're the beam and like push back on it if you want. And then we connect the screws. So that's sort of like where we are right now. And we've been working like over the summer on a number of experiments related to force feedback that will help the robot basically be able to find more dynamically the plane. And we think that this is a really promising strategy because if we're able to place the hanger like pretty accurately, especially in relation to the top edge of the beam, which is obviously the goal, then we can actually use much more standard methodologies to have like, for example, the robot screwing find the holes that are already in the connector. So we know that the connector holes are accurate. So we'll use those like in the secondary step with the screwing. So for the screwing, we've also like done a lot of research about what is possible with this. The short story is that like actually no one is really automatically screwing that we know of these long screws, like 3 to 6 inch lag screws. And we're working with Weber and a couple of other people on either buying one of these machines that we can modify to try to do this, where we can really take advantage of not force feedback, but we can like read the torque values and we'll be able to do this a little bit more adaptively. And we also have figured out that that this is going to be really challenging. So like screwing in timber is not like screwing in metal, where a lot of these systems have been developed, but we're pretty confident that we'll be able to like use some of the advances in motor control and feedback to try to solve this problem. And we've also gotten a lot of feedback that it's like a problem worth solving because it does pose a long-term occupational health issue for putting in these screws, and it's also can be challenging for companies to get long-term labor to put in the screws. So we're diving into that like now sort of while we are developing the new method for the placement. And yeah, so we also have some little advances in these in the placement with like the actual hanger, which is a bit heavier. And this is what you can see later in the lab. So again, it's going in like finding the hole. It's very fast. We actually slow it down here so that you can kind of see. And then pardon my video. Yeah, then it asks like, have you placed the hanger? Then you would place it and then it goes away. And another thing we've done really quickly with industry is looked at like in the future. So if we are able to develop this, we are planning to like try to pilot it at the end of the second year of this project in some capacity. But we also understand that this would probably fit within a larger system of like automated tools for post-processing steps. And so we've been doing some like quick digital investigations as to what those might look like. Some might seem very standard, like the one in the top left, where this system is mounted on like a rail of industrial robots, and the parts are put there, and people could potentially be working on other aspects of the beams while the robot is operating in one area. Others are probably less conventional, like AGVs driving around that are bringing the screws to each one and putting it in. Or the one that I like the best is where the robots are actually like riding on the beams. So they actually use their they use the beam as part of their location and movement system. So I think we have still a lot to do in the second year, but we've made some pretty interesting progress, and we have a lot of interest from industry. Thanks.